Welcome to Pre-Calculus. Today we will investigate polynomial even degree functions, focusing on graphing and analyzing for domain, range, and end behavior. We'll take a look at two examples. Our first example is a quadratic function. Our instructions say sketch the graph of each function, including a table of 5 values. So we'll graph our function by using a table. Once we have our graph, we want to identify domain, range, and end behavior. So I want to make an initial prediction as I look at this quadratic function, negative x squared plus 6x minus 4. And I want to make my predictions about what's happening to the two arms of the polynomial function. And really, I'm looking on the left and the right in terms of the graph. But I can make the prediction from the equation before I've even graphed the function. And what I'm looking for, first of all, is what is the highest power on x in the function? What's the highest power on x? And another way we can identify that is as the degree of the function. So I'm going to look at my exponents here on this quadratic function. So I've got definitely a square. I don't have any power listed on the 6x, that linear term, but I understand that to be a power of 1. And on the 4, there's no variable at all, so I'm tempted to say there's no power there whatsoever. I can think that that's a hidden x to the power of 0. We remember that if I raise anything to the power of 0, it has the value algebraically of 1. But when I look at those three powers, the highest one that I've circled is 2. So this function is a degree 2 polynomial. Now, the way that I can use that to predict how the ends of this function on the left and the right are going to behave is based on whether this degree is even or odd. So I see that that degree 2 is an even degree. And what that tells me is that the arms on the left and the right of the function will be approaching the same direction. So they're either opening upward or they're both opening downward. And I'll write that. So that comes directly from the fact that the degree of this function is an even degree. So they open up or down. Now I can make a prediction about which of those is the case for the function by looking at one other key trait. And that trait is the sign of the leading coefficient. So I make that first prediction based on the highest power in x, the degree. I can refine my prediction to say both arms are headed up or both arms are headed down, but looking at the sign of the leading coefficient. So let's identify what that is for this function. I'm looking at the x term that has the highest power. So I'm really focusing in on this negative x squared. And I don't really see a coefficient there. Now, if that's the case, I can write in a 1. And at that point, I see that that leading coefficient, so it's the coefficient on the highest powered x term, is negative. In fact, the leading coefficient equals -1. Now, if that's the case, what I can say is this -1 leading coefficient is going to, in terms of the graph, signify that both arms are going to approach negative infinity. So what I'm looking for on my graph is generally something like that. Now, I don't know where the graph is placed, but what I do know from looking at those two items, the degree of the function and the sign of the leading coefficient, that I can at least say in this case, the parabola opens downward. Well, let's follow up with proof. So I want to graph this function, see if that prediction was accurate. So I'll do so by a table. I'm going to place my x column on the left. And I'm just going to choose the traditional 5. So -2, -1, 0, 1, and 2. That's kind of my go-to set for the domain. And it's a good one to start with because it centers around the origin. For my y column, I'll go ahead and write f of x. And just to remind myself that these are not items that I choose, they're ones I calculate, I'll write the function negative 1x squared plus 6x minus 4. So I want to calculate those y values. I always have a choice whether I want to calculate those manually by inputting these x values and simplifying, or I can go to the graphing technology on Desmos. Now for this task, my preference is the calculator because there's information on Desmos that I might miss in my manual simplification. So let's head over to Desmos, and I'm going to write that function down. So negative x squared plus 6x minus 4, and let's calculate our table of values. So here on Desmos, I'm going to enter it starting with f of x equals negative, I can put the 1, x to the power of 2 plus 6x minus 4. And I can see immediately from the graph that Desmos plots here that my prediction was fairly accurate. I didn't place the parabola in the correct zone. This one I can see is mostly in quadrants 1 and 4. But nonetheless, I do see that both arms are opening downward. Well, let's get our table so that we can make a better, more precise, more accurate graph. So always Desmos starts again with that negative 2, negative 1, 0, 1, and 2. But I see that that's not the most advantageous domain set. And the reason is because at negative 2, my y value is negative 20. And that's true about the function, but in terms of my graph, that's way off my coordinate plane. That's down in the basement. Similarly, at negative 1, negative 11, in terms of an output, is true, but not graphable. So where I can really begin here is 0, negative 4. You'll notice on the graph, that's the first point that I can see on the left. Also 1 is very graphable, 2, 4. But I'm also seeing I'm missing points from the right side of this parabola. In fact, I don't even have the vertex graphed yet. So I'm going to do two things. I'm going to omit these two values, negative 2 and negative 1, that produce ungraphable y values. And I'm also going to extend in the other direction to give more points on the right side of the function. So 2, I'm going to hit enter, get 3, 5. That's my vertex. I can see it appear on the graph. 4, 4. So now it's turned around and is descending again. 5, 1, 6, negative 4. And that seems to be a very symmetrical set in terms of the y values. So those I'm going to record. We'll go with the domain 0 through 6. And the output's negative 4, 1, 4, 5. And then repeated in a reversed order, 4, 1, negative 4. That gives us what we need from Desmos. I'm going to head back to the graph here. And let's adjust our domain just to reflect what we'd seen on the graphing calculator. So we'll go 0, 1, 2, 3, 4, 5, and 6. And then the outputs, just to get those recorded again, negative 4 at 0, 1, 1, 2, 4, 3, 5. And as I see 4, 4, I see that this definitely is my maximum, or in this case, my vertex. So I do see a pattern around it which repeats. That 5 has an output of 1, just like the output of positive 1. 6 has an output of negative 4, which repeats the output at 0. Very symmetrical. So now we're ready to graph our function. We'll get rid of our prediction there, and we'll plot these points. So right on the y-axis, 0, negative 4. In quadrant 1, 1, 1, 2, 4, 3, 5. And here you'll start to see the symmetry as it appears on the graph. 4, 4, 5, 1, 6, negative 4. And once we have that framework in place, we just want to graph the parabola. rises on the left and then descends on the right. And I can very clearly see from this graph that my two endpoints here, so just looking at the endpoints, they are both opening downward. And so my prediction based on the degree and the sign of the leading coefficient was an accurate prediction. So it's good to see that we can make those judgment calls from the equation even before we see the graph. Well, let's now complete this out. We've done the first task, which is to graph the function. Now we need to find the domain and the range. So let's remember, for domain, what we're looking for is a description of the x values of the function. So I'm going to highlight domain there in green, and I'm going to highlight the far extremes of the graph. And where I'm looking, again, I'll put this domain as about x. From the left, my far left x value is negative infinity. If I were to go far to the far left forever, similarly to the far right, I could identify that as positive infinity. And one of the things I want to do to help me write this domain is, just by looking at the endpoints of the graph, I want to make kind of a separation between the vertical travel of the function and the horizontal travel. So on this left side, I see that the majority of the travel is decreasing. But I also notice that there is a left drift to that far left side. So mostly that left side is traveling downward, but it does travel to the left slowly. But as I let that go forever, it will not stop. So I see that really where that function's headed on the left is negative infinity. So I'm going to start writing the domain based on those arrows. Domain here, if I were to write it in interval notation, I'd open parentheses and say this function begins at negative infinity, the far left side of the graph. And then I can do something similar on the right side. So I see that right arrow here on this purple function is also mostly traveling downward. It's descending, but it's also drifting, in this case, to the right. And where that's headed in terms of x is the opposite extreme from negative infinity. It's heading towards positive infinity on the right. And that's how I finalize my domain. So this one, and we can kind of start to expect this from polynomial functions, is the domain includes all the real numbers. One thing we see is we could actually write that as the domain, all real numbers. And as we follow up our investigation with just some kind of essential facts about polynomial functions, that domain is going to always be all real numbers. Let's also consider range. So I'm going to pick up the highlighter again. Range, if I find it here in the words, is a description of the y values of the function. So remember, y values are vertical. We read from the lower part of the graph to the upper part of the graph. So I'll place those two extremes at the bottom and the top. And then I'm just going to describe them like I did with the x extremes on the left and the right. So at the lower part of the graph, I would identify that direction as negative infinity. At the upper part of the graph, I would identify that as positive infinity. Now, for an even function like this, an even degreed function, I'm going to have a cutoff point. And where it is at the vertex of the function. So if I was just to identify it on the graph, I'm really going to kind of focus right there for my range, one of the extremes for my range. Now I can find that y value in my table. We marked it as the maximum or the vertex. So if I label it here on my graph, that point 3, 5, really where I'm focusing is this 5, because that's the y value of that vertex. And the reason I'm focusing there is because that's the highest point on the graph. And that really allows us to write our range. So the range, if I read from the lower part of the graph to the upper part of the graph, the range would begin with arrows that are pointing downward. That to me again says that this function has its roots in negative infinity. As I read up the graph, I see that the function has uninterrupted y values all the way up to +5, which is the y value of the vertex. I'll put that as my last point because I don't see any other parts of the graph that are above a y value of 5. But I have to indicate in my interval notation that the graph actually equals +5 at that point. And the way that I do so is by recording the bracket. The bracket in interval notation says the function actually equals that value. We don't put bracket for infinity because I can never equal infinity. Infinity is a moving number. Well, that concludes domain and range analysis. The last thing we need to do is record the end behavior. Good news is we've really done the work already. We just need to translate. Let's remember what we're trying to say with end behavior. It's really an answer to the question, what's happening to y? What's happening to y? And where we'll get our answer to that question is already recorded here on this graph. We're going to use these pairs of arrows that we drew to help us think about domain and range. And really all I need to do with my end behavior statements is translate those pairs of arrows. So if I start here on the left pair of arrows, I'm going to look at the horizontal one first. So that one that's pointed to the left, what that says is as x approaches negative infinity. So I'm just translating what that arrow is indicating on the graph. As x approaches negative infinity, we write that because negative infinity is to the left. Then I just need to look at the vertical arrow. It's pointed down. So in terms of y value, y approaches the down direction, negative infinity also. We can do the same for the right pair of arrows. So in that case, the horizontal arrow is pointed right. So the way I'm going to translate that is as x approaches the right direction, which is positive infinity, and then I look at the vertical arrow to get my y direction, it's pointed down. So again, y approaches negative infinity. And that completes all of my analysis for this question. Just to bring it full circle, we made a case at the beginning based on the degree of the function and the sign of the leading coefficient that both arms should be pointed down. And really, we've described that in a mathematical language here in my end behavior statements. So if you've made the initial case that, hey, it's an even degree function with negative leading coefficient, what that should say is that these two end behavior statements should be the same, and moreover, they should both be negative. So again, just to make a case for the value of making a prediction before you start graphing, before you start analyzing, it really provides us with a lot of information and confirmation as we go that what we're writing is true. Let me box that statement. Let's take a look at a second example. Just to recap what we've done here, we've graphed the function using a table after we made a prediction. So we made a prediction, brought the table, brought the graph, saw that the prediction was accurate, and then used the graph to write our domain, range, and end behavior, and then circle back around just to say, did the prediction match with my end behavior statements? Well, let's take a look at a second even degree function. So here's a quartic function, a power of 4. Let's get 100% view here. So notice the instructions are the same. I want to sketch the graph from a table and then analyze for domain, range, and end behavior. Let's start again with our prediction. So we know at this time we're looking for the highest power on an x term in the function. So that's going to tell me the degree. So I'm just going to circle the powers here. I've got x to the power of 4 minus x to the power of 2 plus 2. And like we did on our first function, we'll assume that's x to the power of 0. Again, power of 0 would yield 1. So it's kind of a hidden term there, a hidden factor. Well, the highest number that I've circled is 4. So this is a degree 4 polynomial. When I think about that 4 and try to identify, is that even or odd? Definitely the 4 is an even degree. So like our first example, what we'll expect is that would be both arms opening up or both arms opening down. So we'll record that, both arms up or both arms down. And then remember, we can decide which direction based on the sign of the leading coefficient. So if I look here at my function for the leading coefficient, I see again in front of x to the power of 4, there is no coefficient there. So I'm going to write a 1, circle it, and I see that that is positive. So when I notice that I have a positive leading coefficient, the way that I'll interpret that is that that is going to have both arms opening up because the leading coefficient has a positive sign. Again, I don't really know what that graph looks like, but something that has both arms opening up. So I'm just going to put a quick sketch just to kind of record my initial prediction. And then let's follow up with our table. So I'm going to put again x values, -2, -1, 0, 1, and 2. And then we'll calculate our f of x values based on the function. 1x to the power of 4 minus x squared plus 2. We do have the decision again to either calculate manually or use Desmos. And I'm going to again choose Desmos so that I can see, do I have all the information I need from the graph to sketch it well? So let's head over to the graphing calculator. We'll clear out our entry from that first degree 2 function with negative leading coefficient. So here's f of x equals positive 1 x to the power of 4 minus x squared plus 2. And there's our graph. So again, I want to kind of like check my prediction. My prediction was both arms opening up, and I see this graph does that. So it bodes well for the prediction. Let's get our table of values. So again, Desmos is giving us that -2, -1, 0, 1, and 2. As I look at the outputs there, I see that it's a good centered picture of the graph. It's very symmetric. Output -2 is 14, -1 is 2, 0 is 2, 1 is 2, 2 is 14. So that's a good table for me to write down. 14 is going to be a little bit off my graph, but I can estimate where that will fall. But what I'm seeing on the graph as I look at the points that are plotted, I just have these 3 at the level y value of 2. But I'm noticing that there's 2 parts of the graph where I have minimum values, but they're not listed in my table. So Desmos can help with that. And again, that's one of the advantages of using the graphing calculator. I want to find the value of those 2 minima. So on the left, I'm going to just hover the cursor where I believe that extreme value to be. I'm going to click. And Desmos will label that as -0.707. And the output there is 1.75. I can also find the coordinate for the right-hand extreme This is very symmetric. So that's positive 0.707, same y value, 1.75. So I am going to include the table values and incorporate these two extreme points, these two minimum values as well. Well, that's what I need from Desmos. Let's head back to our graph to finalize. I'm going to get rid of my prediction there because I want to graph the actual function, and I do want to incorporate my two extreme points. So I'm going to put these x values, negative 0.707, that's in between 0 and negative 1, and between 0 and positive 1 is the other 0.707, the positive x value. Let's get our y value. So negative 2 is 14, negative 1 is 2. The extreme value at negative 0.707 is 1 3/4. 0 is 2. So I can see there that this is a minimum. So in a way, that's kind of like a vertex. Same for this positive 0.707. That again is a minimum. We can think that this function has, in a way, two vertices. At 1, we have 2, and then at 2, we have 14. So a very even symmetry function. If you remember even symmetry, I have this identical output surrounding the origin. Well, let's graph that function. So I don't have the 14s. I can estimate those. So I'm going to just add some marks, 9, 10, 11, 12, 13, 14. So I am up in the words at 14, but that allows me to kind of see where the graph's approaching the origin from. It's from the far upper part of the coordinate plane. At negative 1, I can graph that easily, though. That's 2. I need to estimate negative 0.707, 1.75. The y-axis intercept, which is 0, 2, is easy to graph, but then I need to estimate positive 0.707, 1.75, 1, 2, easy to graph, and then 2, 14, I got to estimate up here in the words. So I'm ready to graph my function. So this one has both arms very high up, descends, and then has that W shape near the vertex, and then ascends quickly back up into the sky. Let me get a better graph there, guys. So I'm going to just sketch this in parts. Okay, so not a perfect graph, but close. Let's try again. And that gives us a rough shape for our degree 4 function there. Well, that completes the graphing. Let's take a look at our analysis items. So the first thing we want to decide is about domain and range of this degree 4 function. So to help us out again, I'm just going to do some annotation with the highlighter. Let's pick our domain values first. So remember, domain is a description of the x values of the function. So I'm going to highlight domain, and x values again are from the left to the right. So as I look at the two kind of extreme parts of the function on the left and on the right, what I want to do again is just mark the general trend of the function at those extremes. So I see at the far left up here that the main travel is in an upward direction. But like we saw with that first function, is there is a trend to the left. It's not extreme, but it is drifting over to the left as we go. So I see that that left side is going to tend towards negative infinity. Similarly, if I look at the right extreme, again, the main travel of the direction is up, but I am noticing that there's a drift to the right. It's a slow drift, but if I carry that out kind of to infinity, I see that that is headed towards the far right, which I'll identify as positive infinity. So my domain, as I begin to write it, is going to describe that left and right drift. And what this falls in line with is really our kind of what we said in our last example, that all polynomial functions have a domain of all real numbers. And that, in interval notation, negative infinity to positive infinity, describes exactly that, all real numbers for my domain. So that was a description of the x values. For our range, we'll consider a description of our y values. And that, again, is from the lower part of the graph to the upper part of the graph. And when I think about those extremes, the lower part's negative infinity, the upper part is positive infinity. And because this is an even degree function, I'm just remembering, okay, there's going to be either a starting low point or an ending high point. Now, since this one had a positive leading coefficient, I see that it has basically a minimum value here. So with the highlighter, I'm going to highlight those minimum, and where I'm going to find that number is in my table. So remember, in the table, we'd identified that y value of 1.75 as the kind of the starting point of the function. And if I label those points, negative 0.707 comma 1.75, and then on the right, positive 0.707, 1.75. I see there's no other points on the graph that are lower than that y value of 1.75. So what I need to do is highlight that y value. And that tells me where my range begins. So I do need to begin with a bracket, because that function actually equals 1.75 on the low side. And then on the upper side, because I've got those arrows both pointing up, I would say that the range continues to positive infinity. Close that out with a parentheses. Last thing we need to describe is the end behavior. Remember, end behavior is answering the question, what's happening to y? And I'll use those pairs of arrows that we drew to help with the domain and range. So just like we did with the first example, I want to just translate those arrow pairs. What's happening to y? So the first pair of arrows, the horizontal is facing left. So I will translate that as x approaches, left direction is negative infinity. The vertical arrow is pointing up. So I'm going to record that as y approaches, up is positive infinity. Now I'll just translate the second pair of arrows. That horizontal is pointing to the right. So as x approaches, the right direction is positive infinity. The vertical arrow is pointing up, y approaches positive infinity. And just to bring it full circle, recall our initial prediction was that this is an even degree function with positive leading coefficient. And what we had said was that should have both arms pointing up. And the way that we see that prediction followed through here in our end behavior statement is that these y values are both headed towards positive infinity, and that aligns perfectly with us saying that both arms should open up. And that concludes our second example here of graphing and analyzing an even-powered polynomial, even degree polynomial, for domain, range, and end behavior. Thanks for joining for this graphing and analysis. I'll let you graph and analyze your own even degree polynomials. Thanks for joining. See you soon.